We now come to the Laplace transform, which is one of my favorite parts of differential equations. So, before I start gushing about why it is so cool, let me introduce to you what it actually is. So, if we take the Laplace, spelled Laplace, but it is Laplace because it's French, the Laplace transform of a function, which is written with a loopy L, like this, the Laplace transform of a function f of t, this is going to equal the improper integral going from 0 to infinity of your function that you're taking the Laplace transform of times e to the power of negative s times t. S is just a number here, dt. That's it. And notice, this Laplace transform, you're taking the Laplace transform of a function which is a function of t, and then the only thing that you're going to get left with, because this is an improper integral, is this s right here. So the Laplace transform itself is going to be a function of s. Okay, so a couple of things about the Laplace transform, and we're going to spend the next couple videos, really maybe 5-6 videos, going over different properties that the Laplace transform has, because it has a lot of properties. And really what you can think of the Laplace transform of is, it's really, at its core, it's an integral with a huge amount of useful properties for solving differential equations and elsewhere, but mainly an integral useful for solving differential equations because of its property. So, useful for solving differential equations, shorthands I won't be writing forever. And at its core, that's what it is, because this integral is chock full of nice properties, and that's one reason I love it so much. So, let's prove some properties. The first thing that is arguably maybe even the most useful, and the reason it's useful at all for solving differential equations, is it's linear. So if you remember our discussion of linearity when we were talking about second order homogeneous and particular solutions to second order differential equations, what it means to be linear is that if you have the Laplace transform of some constant, k sub 1, times some function, f of t, plus a different constant, k sub 2, times a different function, g of t, if the operation, the Laplace operation, the Laplace transform, if it's linear, then this should equal, we don't know if it equals yet, it should equal k1 times the Laplace transform of just f of t, plus k2 times the Laplace transform of just g of t. Okay, so this should be the case. Now let's actually prove that it's the case given this definition that I gave you up here. Okay, so the Laplace transform of this, I'm not going to rewrite it, but it's going to equal the integral from 0 to infinity of the function f of t. In this case, our function is quite big, so I'm going to just use some parentheses. k1 f of t plus k2 g of t. That's the entire function that we're plugging in. It's this sum times, and then this part now, so times e to the negative st dt. Okay, but we know that multiplication itself is distributive, so let's distribute out this e to the negative st, which is going to get us to the integral from 0 to infinity of k1 f of t times e to the negative st, and then plus k2 g of t times e to the negative st. I just distributed this e to the negative st to each term inside the parentheses, dt. Okay, now we know by addition that the integral itself is a linear operator because the sum of two functions integrated is the same as the integral of each function just summed. So we can rewrite this as the first integral, the first term of this sum plus the integral of the second term of this sum. So integral of 0 to infinity k1 f of t e to the negative st plus k2 g of t, plus the integral from 0 to infinity of k2 g of t e to the negative st dt. And finally, because we know that we can factor out constants here, we know that we can say, and I'm going to switch colors because we're nearing our incredible finale, we know that we can take out this constant, and what we're left with then is k1 times the integral from 0 to infinity of f of t times e to the negative st dt. I forgot a dt here. Alright. Plus, when we factor out the k2 now, the integral from 0 to infinity of g of t times e to the negative st dt. And what is this? This is the Laplace transform of f of t. If you remember, we have f of t, e to the negative st, 0, infinity. It all lines up. This is the Laplace transform of g of t, because we have g of t times e to the negative st from 0 to infinity. It's all lining up. So what we're left with is that this equals just k1 times the Laplace transform of f of t plus k2 times the Laplace transform of g of t. Alright, we're going to have to squeeze it. I'm just going to do the Laplace transform of g. And this is exactly what we wanted to show. So yes, indeed, the Laplace transform is linear. So I'll write it up here. That the Laplace transform is linear. And as we go about proving other properties about the Laplace transform, this linearity is going to be useful. Okay, well, I'll see you then.